Welcome back. Um, we're talking about chapter 13 of ACI 318-14, right? And this is about foundations. Covers both the shallow and deep foundations. But then there's really not too much into the in this chapter. I mean, you have to design your reinforcement for a different chapter, treating it as a one-way slab or a two-way slab. You determine your thickness based on previous concepts discussed here, right? Um, the cover for the foundation comes from a different chapter. So there's not too much in this particular chapter. So we'll not be opening ACI code or going to this chapter, and we'll not be talking about all those concepts. But we will do some more worked out examples. If you have not watched my previous session, we did talk about the concepts in detail, mainly the difference between the net bearing net allowable and factored net base pressure bearing pressures, and why they are important. One needs to clearly discriminate between allowable bearing stress, gross bearing stress, net allowable bearing stress, factored net bearing stress. Otherwise it becomes very hard to do these problems. It becomes confusing and hard to do these problems. Okay, so we talked about all those in the previous session. Again, I do these videos because the structural codes are often very heavy on text but very light on visuals. My goal is to take these dense, complex clauses and bridge the gap with simple hand-drawn sketches, and you will see me doing um, not pretty sketches, but then the chicken scratches, right? But then the idea is to just convey the translate the text into picture so that you can visualize it, right? This visual association makes it much easier for you to recall specific requirements when you are under pressure in an exam setting. In this video, we are breaking down chapter 13. In fact, we'll be doing more worked out examples on chapter 13, right? We did a few worked out examples in the previous session, so if you have not watched that, feel free to go ahead and uh, take a look at that uh, section. Okay. All right. So let's get to our first problem here. So the first problem is about footing design. I'll call this problem 2, but then let's see. Um, in this problem, we'll talk about how this is a wall footing, but then we'll talk about how we should decide the thickness and all that. Okay. So let's see here. So here is let's read the problem statement. Problem: design a wall footing to support a 12-inch wide RCC wall. RCC is reinforced cement concrete. So the picture of this footing is something like that, right? So it's a spread footing. This is the wall. Obviously, the wall thickness is like 12 inches, right? Then there is dead load and live load. So there is a P dead, which is 20 kips per feet, and there is a P live, which is 15 kips per feet. At the bottom of the footing is 4 feet below the grade. That means there is some soil, right? So that let's represent that as the soil. And then the bottom of the footing, which is here, is 4 feet below grade. Okay. And then gamma soil is like 100 lb per feet cube, right? And then gamma concrete, reinforced concrete. So let's say 150 lb per feet cube. Correct. And then from the geotechnical report, looks like the geotechnical engineer says that the Q allowable, right? That's important. Q allowable is 4 KSF. So if anything beyond 4 KSF, then the soil is gonna fail, or the factor of safety will get reduced. Obviously, when they give you this much, they also include a little bit of factor of safety there. They are saying no appreciable sulfur content. That means they are talking about the cover. So they are saying that okay, the soil is doesn't have a lot of sulfur, so you decide your reinforcement cover based on it. So there's a chapter in ACI. If you go to the cover section, if your footing is underground, exposed to soil or buried inside soil, and then there is sulfur content, you pick up your thickness differently compared to a case wherein there is no sulfur content. Okay, then the reinforcement Fy asking us to use 60 ksi reinforcement, and Fc prime, this is indicative of strength of the compressive strength of the concrete. So 3 ksi. Okay, and this is normal NCW concrete. What that means is your lambda value will be 1.0. We talked about all these details. If you have not watched what Fc prime is, if you don't know what why lambda value affects the strength of the concrete, feel free to go to the previous sessions and then start from some basics there. But then this is the problem statement. So what is that we need to do? We need to design the wall footing. That means we need to decide the thickness, correct? What is this thickness? We need to decide some reinforcement and do a bunch of checks. Okay, so let's get started. Solution. The first thing we need to do, if you have watched my previous classes, you have to decide the area of the footing. That means if you look at this one from the plan view, we want to decide how wide this is, what is this dimension, and what is that dimension, right? And here is let's say here is the column there. So that is your column, and this is just the plan view of this detail here, right? So how do you decide that? Area has to be decided based on something called Q net, because Q net is the loads that you are unfactored loads that you are applying divided by your area. So if you know Q net, if you know the loads that you are the unfactored loads that you have, then you can decide your area. So how do I find Q net? Again, look at my previous video. I gave you some illustration. I provided a bunch of um, sketches, and then I clarify all these concepts. But then Q net is nothing but Q gross minus the overburden pressure. In this case, the overburden pressure is because this is um, I mean, we'll have to make an assumption because we don't know the thickness. So let's assume that this is a 12-inch concrete. Let's assume the thickness, and we'll go ahead and check the thickness and all that. So that means this is 3 feet, right? So the overburden pressure to find your Q net, you take the Q gross and subtract the overburden pressure because of soil and overburden pressure because of the concrete footing, right? So that is because the soil, I mean, the footing has certain weight and the soil also has certain weight. To find your net bearing pressure, you subtract gamma soil times of the depth of the soil plus gamma concrete times the depth of your concrete. Okay, so again we started with the assumption that the overall depth is 12, something like 12 inches. Okay, so overall depth is like 12 inches, which is equal to 1 foot. So 1 foot of concrete, whereas 3 foot of soil. So this is nothing but your 4000 minus gamma soil is 100 times the height of the soil is 3 feet plus gamma concrete 150. The height of concrete is 1 foot. What height are we talking about? We are talking about this, not about the stem. The weight of the stem is ignored, or a part of the dead load, something like that. Okay, so you subtract this is called overburden pressure. Overburden pressure from the gross, you get your Q net as 3550 PSF. That is your Q net. Okay, make it bigger. So 3550, we got our Q net. Okay, so now what we do is, like I said, Q net by definition is your factored load. That means your unfactored load, dead load plus live load divided by area of the footing. Why is that? Because the dead load and the live load, they are the ones that are causing pressure underneath the foundation. Okay, so you decide your area based on that. So this is nothing but your the dead load times factor 1 unfactored, of course, live load, right? Times by area of the footing. You are assuming that the area is sorry, this is a wall footing. This is not a so this dimension you are assuming as 1 foot, right? And then you have to decide this. In other words, the footing, the wall is like that, and your footing is like this, and you are designing uh, this setup here. Here is your soil. This depth is 3 foot, 3 feet. This is like 1 feet, 1 foot. Okay, so this is all concrete. Everything here is soil. That is all soil. So we are designing, we are not deciding this dimension. We are just assuming that this is a 1 foot dimension along this direction. So we are taking a strip. This is 1 feet, right? And then we are deciding this one. So 1 feet. So this area, the plan area of the area that we are designing is 1 feet by b times of 1. So your area footing is b times of 1. But you know that your Q net is equal to 3550 PSF is equal to um, 45 divided by your B. So your B is 9.859. Obviously, we can't communicate that to the contractor. So we say that provide B is equal to 10 feet. Okay. So that's about the Q net. And there's another important concept again. We talked about all this last time. So if this is new, this sounds new to you now, then you'll have to go back to my previous video session or whatever. Okay, so that is called Q net, but this is the factored Q net because this is the value. I mean, footing is made out of concrete, and concrete design is per LRFT, and you want to understand the forces, the factored. I mean, the soil pressure is acting like that. For example, on that section, right? So you want your value to be a Q net, but then you want this to be a factored pressure. That's why we're calculating the factored pressure, and that is nothing but the factored load. This is the factored dead load, and you're also factoring your live load with 1.6. Sorry, this is 15 times of 1. So you're factoring the load and you're considering the area provided. The area required was only, width required was only 9.59, but we provided 10. So you take that. So from there you calculate your Q net factored as 4800 PSF. This is Q net, but it is Q net factored. Correct? So found out that. So then we need to calculate, you need to check the depth. We have already decided on we assume that your depth of the concrete is like 12 inches. So we need to see if this is sufficient, meaning we need to see if this depth can handle the one-way shear. Okay. So now let's talk about one-way shear. So we are checking. We're trying to see if the depth assumed will meet the one-way shear requirement, right? So what happens to one-way shear? Now this is your 1 foot length, right? Discontinuous like that. I'm looking at the footing from the top view. That's your that is your column, and this width is like 10 feet, right? Obviously, the picture is not proportional, not up to scale. So 10 foot. This is only 1 foot. One-way shear, for one-way shear, the critical section is at a location at this location, right? Which is at a distance D from the face of the support. That is the face of the column, right? So that is the face of the column, D from the face of the column. That is where your one-way shear happens, correct? And why do we have to locate that section? That is because we want to know how much uplift is happening. So let's say here is the column. Let's say this is the section. Critical section. We want to calculate what is the shear at this section. Now to calculate the shear at that section, you need to know, if you take a free body diagram on the left. So this is the pressure acting on it. What is the pressure? The pressure is Q net, net factored. So Q net factored is acting on what area? Q net factor is acting on this area here. Okay. So we know the length because that is arbitrary 1 foot. We're designing a wall footing. Whereas this width is what we need to calculate. So let's call that with x. So your x plus, this is a d from the face of the support, effective depth from the face of the support, plus half times the column. That means you are here, half times the column width, which is column width was 12 inches, correct? So by 2, those many inches is nothing but half of 10, right? So half of 10, which is from here to here, is like 10 by 2. So this is nothing but 10 feet by 2, or 5 feet, or 12 5 60 inches. Okay. So how did we get this one? This is nothing but adding. We know the dimension from here to that edge as 5 foot, and you're calculating, you want to find out your x, but you know that the critical shear plane is at a distance d from face of support. So d from face of support plus x plus half the depth of the column should be my half times of 10. So you do this, and you will find out that x is equal to 45.5 inches, right? Now again, what is x? X is, if this is the if this is the critical plane, x is that dimension from here to here, 45.5 inches. What is the use of this? Once you know x, you know that x, which is 45.5 times your or 45 times inches by 12, so that is in feet, times 1 feet, so that is your area. And then on this area, who is acting? Q net factored is acting. Q net fact, that is acting, and that means this value is 4800, correct? So you do the math there, and you find out that the factored shear, or let's call it VU, the factored shear is nothing but the area. This is the area times the pressure, right? So that is close to 18.2 kips. So in other words, VU is 18.2 kips. What is VU again? VU is the push from the soil on that part. So the push from the bottom is 18.2. Why do we have to find that? This push has to be resisted by whom? Resisted by the by the thickness of the concrete there, because this is shear, so shear has to be resisted by the thickness. Okay. So if this is the factor load, what is the strength of the concrete? We know that the strength of concrete is phi times Vn, right? So phi times of what is your Vn? 2 lambda square root of Fc prime into B times of D, right? If you don't know this equation, if you need to understand this in a little clearer way, then you will have to go to my previous videos. But then real quick, here is the slab, right? And we found out that the shear on the slab, somewhere here was our critical section. So that is my critical section, correct? That section will resist a shear force of 18.2. There's a 18.2 force coming, pushing the thing upwards. So so the resisting area is B. So this is B, let us say, times the D, right? So that is the resisting area, and here is the shear stress that concrete can take. So if you do this math again, phi for shear, you cannot, in an exam setting, you cannot go check all this from the code. So you'll have to remember phi for shear is that much, phi for bending is roughly, if it is tension controlled 0.9, then it goes down if it is not a tension control session, and you need to do some extrapolation, right? Because it is the factor is like that, correct? So this is your 0.65, and this is your 0.9. Y-axis you have your phi value. X-axis it is epsilon s. This is the strain in the steel. So if the tension control, you are in this region. So somewhere there it is 0.9. Okay. Anyway, we talked about that also in a decent amount of detail in our previous uh, um, beam chapter. So go there if you want to understand. Okay, so keep going. Let's keep going. 0.752 times of normal weight concrete times of 3000 psi concrete. Breadth is 1 foot. Depth is my effective depth, right? How do you find the effective depth? We know the total depth as 12 inches. That's what we assumed, right? So 12 inches is the depth of this entire thing. That is 12. But then the reinforcement is somewhere there, correct? So that means there is a clear cover of 3 inches because the soil is not exposed to sulfur content, and then there is a diameter of bar. So let's assume this diameter of bar as 8 inch for now. We'll have to find out if that is suitable or not. So that means you take the total depth, deduct the clear cover, deduct half the diameter to find out your effective depth, which is small d. So small d is total depth minus 3 inches cover minus half the diameter of the bar. Okay, diameter of the bar in this case 8 number 8 is 8 inches by 8, which is 1 inch. So if you do that, then you find out that your effective depth is 8.5 inches, right? So what do you do with the depth? Plug the depth into this equation. So the shear strength is 0.75 times 2 times 1.0 times square root of 3000 times your B is 1 foot, because we are talking about a 1 foot strip in this direction. B is 1 foot is 12 inches and effective depth is 8.5 inches. So if you do the math, you find out that this is only 8.38 kips. So this is phi Vn. Okay. So phi Vn is nothing but the nominal strength times resistance factor. Now the basic rule in concrete is Vu should be greater than less than Vu should be less than or equal to phi times of Vn. But our Vu was 18 point something 2 kips less than, but this is, I mean, our phi Vn was 8.38 kips. So this condition is clearly violated. That means we are not okay in shear. So the depth provided is not good in shear. So what you do, since the depth provided is not good in shear, you restart. So assume now that the depth is, let's assume that um, you can assume any depth, but depth more than your the previous depth, because previous depth at 12 inches was 8.5 inches effective was not good enough. So let's assume that 18.25 is my effective depth. You can do 20, you can do 21, okay, but the procedure remains the same. So there's no reason why I picked 1825. So 1825, or we can do this. We can calculate the, let's say, we can calculate the depth required from shear, right? Because we know that Vu is equal to phi times of Vc, which is we know Vu is 18.2 kips. We know phi Vc as phi is 0.75 times Vc is 2 lambda 1.0 square root of Fc prime times Bw is 1 foot, which is 12 inches, times D. D is D required. D required. Okay, we know that this is 18.2 into 18.2 kips. That means that much. So you find, you can find the only unknown here is D required. So D required is in fact 18.25 inches. So that is the depth required. Okay. If that is the depth required, effective depth required, then the total depth required would be 18.25 plus you add your 3 inches clear cover plus half diameter of your number 8 bar. That is nothing but 8 by 8 inches. So this would result in 21.75 inches depth. So that is the total depth required. But we can restart. We can restart with and let us assume that D is equal to 20 inches. Yes, that is required, but then you will see what I mean. So let's assume that D is equal to 20 inches, because the width of your so again, this is the plan view of the entire thing. We are not considering this direction, we are not considering this direction, we're considering just a 1 foot strip in that direction, right? Then this is like 10 feet, correct? Remember, the critical section is a critical section for shear, one way shear is a function of your small d also. As d becomes, so this is where this is the critical plane, correct? So as d becomes larger, your critical, this area will also shrink, because the critical plane is d from the face of the support. As d becomes big, the plane is shifting to the right, it's moving to the right, and then that area is getting reduced. Okay, so you have to also have that in mind, and you don't, that means you don't need 21.75. So you restart with this much. So that is your depth. So when you provide that depth, what happens is your Q net will change. What is your Q net? Q net is the 4000 Q gross minus overburden pressure. So overburden pressure is nothing but, so here is our configuration now, right? Nothing has changed the other than the, so this is 4 feet, but then so let's say that is 4 foot, and then this is 20 inches, which is 1.667 feet, 20 inches, right? And this is where your soil is. So that means your soil is only 2.33 feet. Okay, why did these numbers change? These numbers change because we revised our depth. So Q net is Q gross minus overburden pressure. Overburden pressure is due to 1.667 feet of concrete plus 2.33 feet of your soil. Okay, so this is nothing but Q gross minus overburden pressure. So this will result in 3517 PSF. That is your Q net. Okay, so now what you do with Q net? P by A required is equal to your Q net, correct? Which implies you know P. What is P? P is 20 dead load plus 15 live load divided by your 3517, which is your pressure. You're taking P, you're dividing that the Q net with that to find your area, and that results in an area of 9.95 feet square. That is the area required. But we know that we are talking about a 1 foot strip in that direction. So that means our breadth required area is nothing but B times of D is 1 foot, right? So breadth required is 9.95 feet. So let's provide a breadth of 10 feet. So the breadth did not change because our depth assumption, which is good. Um, okay, now we have to go back and check, calculate your Q net ultimate, net factored. How do you find net factored? You take the factored load, which is 1.2 times of dead load, 1.6 times of your live load, right? Factored load divided by the area provided. What is area provided? 10 square feet. 10 feet square. So by area provided, so you get your um, that value as 4.8 KSF or 4800 PSF. So that is your Q net factored. Okay. So we have our Q net factored and we have our Q net. Now, yes, we did provide a depth of 20 inches, but what is, so depth is 20, which implies the effective depth is the total depth minus cover minus half the diameter of my number 8 bar, which is 1.0, correct? So your effective depth is 16 and a half, though you provided a depth of 20 inch. The shear resistance for the depth that comes into the play when it comes to shear resistance is only 16 and a half inches. Okay. So now what happens to my, we'll have to see if this depth is good in one-way shear, right? So we have to find out if our one-way shear is good. So that is our, where is my one-way shear plane? Here is my column, one-way shear plane, critical face D from the face of the support. This is D, which is 16.5 inches from the face of the support. So what is this value, right? Again, same story, X, that is that spacing, plus your D, which is 16.25, plus half the diameter of the column, half the dimension of the column, which is 12 by 2, is your center, is your this distance, which is 10 by 2, which is equal to 5 feet. 5 feet times 12 in inches. So your X is nothing but 37.5 inches, right? So because the depth has increased, the critical shear plane has shifted to the right compared to the last time. Earlier this was 45 point something. Now this came down to 37.5. So the smaller the area, the lesser shear force it is going to attract. Okay, so that's why we did not provide an entire depth. So how do you calculate your VU? VU is nothing but, if this is the thing again, that is the shear critical shear plane. So VU is acting on that portion, correct? So that is Q net factored times this hatched area. Q net factored is 4800 times the area of that hatched portion there is 30. It is 37.5 wide times one. So this is 37.5 inches by 12, which is that many feet times 1 feet. So you will find out that this is roughly 15,000 pounds. That is the uplift. This is the demand, right? This is the demand, which is soil is demanding that much. Now, what can your concrete take? Phi times of VC 0.75 2 root FC prime 3000 lambda is 1 times your breadth, the depth of the concrete. Sorry, this is the breadth and the effective depth of 16.25 inches. Okay, so that is close to 16.27 10 cube LP. Okay, so you see that VU is now less than phi times of VC, because phi VC is that much, VU is 15. That means we are good or okay, whatever. So now that means the effective depth that we provided is in a position to handle, concrete is in a position to handle the shear. Okay. Now once you decide shear, how do you decide your AST required? Right. So that means you have that, you have this. Yes, your footing, the depth provided 20 inches is good enough, but what is the area of steel that I need to provide? That depends upon. Now the critical section for bending is somewhere there, correct, at the face of the support. So that is the critical section of bending, and your Q net is acting on that area now. Q net factored is acting on that area. So what is that area? We'll find out the area. You net multiply Q net factor, and then the lever arm is there. So roughly that is acting there. So the lever arm is nothing but this distance by 2. Then you calculate your moment based on that. Right. So let's calculate the moment, and then we come back to area of steel required. So moment, this is ultimate because this is coming from QNet factored, correct? So your QNet factored is 4,800 PSF times the area on which this is acting, right? From here to here, from the center to that was 5 feet. So 5 feet minus half a feet of the column, that is the clear span. Clear span is 4.5 feet. So Q times of 1 is your this entire thing is your upward force times the lever arm, which it is 4.5 by 2. Why is the lever arm 4.5 2? Because the force is acting there, and that distance is nothing but 4.5. This whole thing is 4.5 from the center divided by, so from the face. This is 4.5 by 2. Correct. So that is your force. So you calculate this moment, you will get 48,600 lb feet. So that is the moment coming onto the thing. Okay. So when you have a beam subjected to a moment, and the B, the D, and the phi factor, and the mu, and all that you need to find is your AST. One way of doing it is you assume J times of D, which provides a tension controlled section 0.962. JD is 0.962 times of D. You assume make that assumption, and then end up with a tension control section. The assumption of a tension control section is important because you assume your value of phi as 0.9. The other way to do the same, to achieve the same task, is to find out this ratio mu by phi b d square. So this ratio, if we calculate that ratio here, you will find out that the mu by phi b d square is close to 198.3 psi. Okay, so mu, mu, this is mu, and then the phi, the b, correct? Because you're taking 1 foot normal to the screen, 1 foot section normal to screen. The d is the effective depth. You plug all those values, then that is your mu. Okay, now you can go to your PE handbook, and then if you go to, let's go to the beam section here. There should be a table which will document. There is beam concrete. Sorry, you have to go to the concrete section, and you see these tables here. Here, for example, see if you can calculate the mu value. Let me highlight that. So if you can calculate mu by phi bd square, and you know your grade of concrete is 3000 psi, correct? And you know the steel is Fy 60. That means this table is applicable because your steel is 6010 cube. Your grade of concrete is 3000 psi PSF. The value documented here is your mu by phi bd square. So all the values in the column is that value, and that was close to, when we did our calculation, it was close to 196 or something, correct? 196 point sorry 198.3. So you go here and pick up 195 198.3 value, close to value, something close to that, which is 200 in this case. That means if you provide this much reinforcement, this is the rho, which is AST by B times of D. If you provide that much reinforcement, then um, then it will result in a tension controlled section. That means your assumption of phi is equal to 0.9 would become valid, and you don't have to come back and then plot the strain diagram, check the strain in tensile steel, and then make sure that everything is under control. Okay, so that is how we use this particular table here. Again, one last time, when you have a moment, you know the breadth of your beam, you know the depth of your beam, you know the phi factor. You want the phi factor to be 0.9, means you want your beam to be in a tension control zone. Then you then you use these values and compute something called R. The R is nothing but mu by phi b d square, right? And based on the steel, based on the FC prime of concrete, you come to this table here, find out the approximate value that is closer to your mu. In this case, this was 198, so there's nothing here, so we picked up 2000. And if you can provide that much reinforcement, percentage of reinforcement, if there is this much, then your assumption about tension control is valid, and that reinforcement will make sure that the beam can take that moment here. Okay. So that's how we may make use of that, and we find out from here, we find out the percentage of the reinforcement. Rho is 0.0035 or something like that. Okay, so you know the percentage of reinforcement, you can convert it into rho by B. So rho is nothing but AST by B times of D, correct? So this is AST is the question mark. So AST is nothing but rho times of B times of D, right? AST is nothing but rho is the 0.0035 times your breadth of the beam is 1 foot, right? Let's say 12 inches, and your depth of the beam is we know our effective depth is 16.5. So you'll get your AST required is 0.68 inch square. Okay, so what did we do? We found out the moment that was acting on this piece, right? Moment that was causing the moment that is happening at critical section 2, that is in that direction, that mu, we found out that value as this much. Then we use the tables that were in the PE handbook to find out the area of steel that is needed to meet that requirement. Okay, so now whenever you provide area of steel, you need to compare that with the minimum area of steel. Is my area of steel provided greater than the minimum required? Okay, so AST minimum, we talked about this many times, so I'm not going to go back to the code, but that is nothing but a maximum value of 0.0018 times 6010 cube divided by the Fy you are using. In this case, this is also 6010 cube times your A gross, or it is 0.0014 times of A gross, correct? So your A gross and all that is nothing but 1 foot wide in this direction, and effective section, effective depth deep in the other direction, right? So that is your A gross value. So Ag is nothing but your depth times effective depth times of 1 in this case. Okay. If you're talking about a beam, then it is this would be the width. This dimension would be the width of the beam. That is the depth of the beam. So from here, the maximum value appears to be only 0.432 inch square. So AST provided is greater than AST minimum. So we are good. Okay. And based on the AST required, you can find out. You can come back here and so let's say AST required is 0.68 inch square. So you can take, so that is your, so that is one thing, and then this is the width, that is the width. So let's say this is 1 foot section. Your main reinforcement, let's say this is the, I'm drawing the top view. The main reinforcement has to run like that, correct? So that it can take this moment here, it can take that moment, right? So I mean, based on the area of steel, you assume a 7, let's say you assume this spacing to be 7 inches, right? If you provide number 8 bars at that spacing, then you will meet the requirement. Okay. So provide number 8 at, how do I know that? You can just, these are basics. So 7 inches. You just find the area of 1 bar and then figure out how many bars you need within a 12 inch spacing and provide that AST. Okay. Now the only thing left now is to figure out how much development length, how much I mean, if this development length provided is good enough or not. Correct. So for that you need to understand if your bar, you need to know if your bar is in tension or compression. Obviously here is the footing, right? Here is the footing. We are talking about this bar and trying to check the development of length of that bar, right? This has some side cover, this has some spacing, correct? We need to check if that LD required. Here is a critical section, correct? So this is the critical section. That is where you need your reinforcement, and you need to make sure that on this side you have a length of reinforcement greater than development length, and on this greater than or equal to, on this side you have the length of reinforcement to greater than or equal to development length, correct? So if you go to how do you find your development length? You go to ACI. Development length is what? Reinforcement details. You go to development is 25.4, correct? I don't have a linked copy. So development length of what? Of deformed bars. In what? In tension, right? So development of deformed bars in tension. Why is the deformed bar in tension? Your reinforcement is like that, correct? And the QNet ultimate fellow is pushing from the bottom, right? And my slab is trying to bend like that. That means the reinforcement here that I provide would be under tension. Okay. So when that happens, you can pick up your value from here. There is also a detailed method of doing it, which is this one here, right? So in we can use this formula in our case. The only new thing here compared to the formulas in this table are, you will see that you will see new factors called CB, KTR, and that's it. So CT, CE, that is I mean CE, if are the bars quoted? No, so that means you don't have to reduce it. So CE factor is equal to 1. CS and CT. So let's go check what CS and CT are here. So you go here. CE is epoxy coated. We don't have anything, so that doesn't reduce. Imagine you have a bar like that, deformed bar like that, right? You have a deformed bar, and you apply some oil onto the deformed bars and come here and then start to hold this bar with your fingers right there, right? And ask your friend, those are your lovely nails, right? Ask your friend to pull the bar. Then because there is that epoxy coating on it, it will slip easily. So you need a longer, you need a wider wrist, right? Maybe you want Hulk Hogan, you invite him and then ask him to hold the bar because his wrist is much wider, right? The analogy here is wider wrist is nothing but greater development length. Okay, so CE is 1 in this case, and CS is size factor. We have a number 7 bar and larger. We assume a number 8, so that is also 1. And CT is a positional factor. In our case, the bar is here, and below the bar there is 12 inches of concrete is not existing. Right? There is no below the bar. You just have a cover, and then that's about it. Right? So when that doesn't happen, then it is in the other's case, and your CT value is equal to 1.0. Okay. So if we have to use this formula again, the CT, CE, CS are all 1.0. That means that we don't have to reduce anything. And the only thing we need to find is CB. CB, if you read somewhere here, CB is a factor that represents the least of the side cover, the concrete cover, um, and or 1/2 of the center to center spacing of the bars. Okay. So that is nothing but your CB is nothing but a minimum of your covers in both direction. Side cover was what was the cover to the reinforcement? 3 inches, right? Or have the diameter of your spacing between the bars. I think that was 5 or 7 inches, 5 inches or 7 inches. Let's say, don't remember that. Now, so that is nothing but 3 inches. So CB is 3 inches. Your KTR can be taken as 0. That is somewhere here to be conservative. Now you start to plug in those numbers. You will find that um, your CB is 3 inches, correct? KTR is equal to 0. That means your development length is nothing but 3 by, I'm just copying that formula here, 3 by 40, 60, 10 cube, right? Divided by 1.0 times square root of FC prime 3000 times all those CE 1.0, CT I think 1.0, and the other one was CS, maybe that was also 1.0, divided by KTR. KTR is 2.5, right? And times dB or something. dB is number 8 bars, so 1.0. So that would result in 32.86 times of dB, 1.0. Okay. But this development length can also be reduced by a factor. So you can reduce the development length LD by a factor which is area provided, area of steel required by area of steel provided, right? So that means you take this 32.86, you multiply your area of steel required was only 0.68 something, but we rounded it off, and we provided some reinforcement at a such standard spacing that resulted in a 0.72 inches square. So you can always reduce the development length by this factor. You reduce that, you will find out that it is 27.5 or 15 inches. So that is the development length needed on either side of the critical section. Okay. Whereas the length available, if you calculate the length available from here to here, so that is your length minus the cover. So that is nothing but you have 10 by 2, right? Minus your half the length of the column, which is 6 inches, minus the cover. Cover is another 3 inches. So this is 43 inches, much higher than 28 inches or 27.5 inches needed. That means the length available here is 43 inches, whereas the development length needed is only 28 inches, right? So that means there is enough development length available. Okay. The last thing is you provided reinforcement in this direction, you should also provide reinforcement in that direction. That is called the shrinkage reinforcement, and that is the AST of that shrinkage reinforcement is just 0.0018 times of your A gross, which will be 0.432 inch square. So number 5 bars, you provide number 5 at 8 inches, you will be good in the other direction. Okay. So that's about the footing problem. We do have one more footing problem. If you are interested, let me know. Otherwise, I want to switch to um, how are we doing our time? We're 50 minutes into the recording. Yeah. So let's go ahead and do the let's talk about retaining walls and all that. Retaining walls. So let's say let's try it here. Okay. So let's talk about retaining walls again. This is also covered in chapter 13, but not um, not enough information is available in chapter 13. So we are not looking at the code and trying to walk through every section, but we'll just talk about retaining walls and do one problem that should give you uh, enough confidence when it comes to retaining wall, right? So what is the retaining wall? It retains soil. Usually it is like that, and it has a footing, and there is soil. The ground on one side is higher than the ground on the other side, so maybe there is soil here, and you are building the structure so that the to resist the push from the soil. When you put soil like that, it doesn't want to remain like this, right? So soil wants to spread out like that. When it wants to spread out, obviously it is creating a force in that direction, right? And that force in that direction is increases with respect to depth. um, so we construct this retaining wall so that that force can be handled and we can retain the soil successfully, right? um, so let's talk about some different loads on the retaining wall, and let's talk about earth pressure. So the main reason we're building a retaining wall is to handle the earth pressure, the pressure of the earth being retained on this side, right? So the earth is trying to apply pressure. Now earth pressure can be either active, it can be at rest, or it can be passive. Okay, and again, this when I say active is not active is a term that is that has to be tagged with the concrete and not the retaining wall itself, and not the soil. It isn't, the soil is not active. The retaining wall is active, meaning the retaining wall is trying to move away from the soil. Let's say the retaining wall is trying to move away from the soil like that, just a little bit, right? This is a exaggeration. When that happens, the soil pressure is relieved a little bit, so you end up with something called, you have to use in your pressure calculations, you have to use something called your Ka for your earth pressure calculations. Okay, and if your soil is at rest, meaning let's say you don't allow this motion to happen, so this rotating motion to happen, maybe you pin it somehow on the top, right? Maybe by tying it to something else. So now you have your earth pressure acting in this direction, but then the coefficient, to calculate the pressure, the coefficient that you will be using is called K naught, right? This is a at rest earth pressure condition. Now, if you if your wall is moving, let's say your wall, let's go back to the active earth pressure case, and the wall is moving, and on this, the soil on this side is going to push the wall. That means the wall is moving towards the soil on this left side, right? Let's say you have soil here till there, then the soil is being pushed by this wall. When that happens, to calculate your pressures, you use something called a passive earth pressure coefficient. And usually these values are they depend upon the angle of internal friction. Let's say you're talking about cohesionless soil like sand, then the coefficient values come from simple formulas like this is 1 minus sine sine phi by 1 plus sine phi, right? This is nothing but 1 minus sine phi, and this is nothing but the opposite, 1 plus sine phi by 1 minus sine phi. Okay, so that's how you can calculate these pressure values. And let's say you have a 30 the soil with a quotient angle of internal friction is that much, then usually these are ranked like this. Your Kp is always greater than your K naught, always greater than your Ka. So Ka is the least, Kp is the maximum, at rest is in between. Okay, so those are the coefficients used to calculate pressure. But now let us see how you calculate pressure. So let's say you have a retaining wall like that, right? You have a retaining wall like that, and there is soil fill to the right side, nothing to the left side. We are building a retaining wall so that the soil doesn't flow from right to left. Okay, so what happens is uh, let's say this total height is h. Okay, I'm not till here, but I'm going till uh, here, or let's say till here is h. There's no soil on this side, assume. So then my earth pressure here will be maximum. Earth pressure at the top, let's say you stick your finger there, nothing is going to happen. But if you stick your finger here, there's so much soil that is crushing your finger, and in between it is linear. So earth pressure is going to vary like that. At the top it is 0, and this is all for cohesionless soils. Cohesive soils, the distribution will be slightly different, but cohesionless soils, it is C is equal to 0, whereas phi is some value between 0 to whatever angle, right? Um, so when that happens, that is the distribution. What is the maximum value here? Obviously, the maximum value is dependent upon the pressure, the height or the depth, and it is also dependent upon your gamma value of the soil, right? Heavier soil, then it's going to produce heavier pressure. But then it depends upon the case. If you're in an active case wherein the retaining wall is not restrained at the top and it can slightly rotate to the left, then you're in an active situation and you find out your value as Ka times gamma times of H. Okay. Now, many times the soil is not empty. Maybe there is some amount of uniformly distributed dead load. So this is Q dead, and there is maybe some uniformly distributed live load. Okay, then these are not point loads, but then let us say they are dispersed on a decent amount of area. So live load, dead load. So what happens is that dead load and live load will also produce a thrust on the soil because they are trying to compress the soil, and the soil wants to move away. Push the wall, and when that happens, there is a uniform pressure because of the uniform dead load. For example, for this dead load, the pressure here is proportional to that value there. Higher the dead load, UDL, then higher is the pressure here, right? The pressure is acting in that direction like that, correct? But then you multiply it with your active, in an active scenario, earth pressure case, you multiply with that. This is the story of the dead load. The story of live load is similar. Acts like that. Uniform live load will produce uniform distribution here, Ka times of Q live load. Okay. So now what are these three forces trying to do? The three forces are trying to push the footing to the left, making the footing to slide, and they are also trying to produce a moment about the footing. Why is that? Why and how? Here is the distribution. That means the resultant of this P1 is acting there. The resultant of this distribution is acting midway. This is P2. The resultant of that one is acting at mid height. This is P3. Okay. So what is your P1? P1 is due to the earth pressure. How do you calculate that? The area of the triangle there. So half Ka into gamma into H square is your earth pressure acting on that direction. Where is it acting? Acting from the base, 1/3 of the height. Okay. So the lever arm is at H by 3. Okay. Now you calculate P2. How do you calculate that? You take your Ka, you just multiply it with your Q dead, that is the width of the pressure distribution here, and then you multiply with the height, that is your pressure. Where does it act? Height by 2. P3, how do you calculate that? This is the pressure. What is the pressure? Ka active times of Q live load, and what is the area of the pressure distribution diagram times H. Where does it act? H by 2. Okay. So what is the moment generated? The moment generated is that times this. So half Ka gamma h cube by 3 for this one. On this one, Ka qd h square by 2. For this one, Ka qd, sorry, q live h square by 2. Yeah, so force times distance. Nothing fancy there. So P1, P2, P3 are the forces, and M1, M2, M3 are the moments, assuming this is a cantilever retaining wall, right? But if you have a retaining wall like this, but then it is pinned in this direction here, um, and then you have all the same P1, P2, P3 forces, then you treat this end, because there is reinforcement going into concrete. For shear calculation, you can assume that this side is pinned, but for bending moment calculation, you assume that you assume as if this is a proper cantilever, right? So this side it is fixed, and it is being exposed to earth pressure. It is being exposed to your uniform Ka times of Qd, and it is also being exposed to your Ka times of Q live load. Right, so those are the forces, and you can go to your PE handbook. PE handbook, you will have a formula like that. For example, I'll show you that in a moment. But then, if you have a force P acting at a distance A and at a distance B, what is the moment, what is the reaction here, are all available in your PE handbook. Correct. So if you have a retaining wall scenario like this, wherein the top is pinned and it is subject to P1, P2, P3 forces, you have P1, P2, P2 because of this, and P3 because of this. Calculate the resultant of P1, P2, P3. Maybe it is acting at a certain distance A from the fixed end. So from A, so plug and check those values and find this reaction and find that moment, right? And you, let's say moment is some xxx kip feet, and shear is some xy kip feet. Then you come back and check if your section can take that bending moment. Okay, we'll do all this. Don't worry if you're. I mean, I'm just rushing through because of time. But then we will do a worked out example wherein all this will be explained in a. We'll do a step by step process. Okay. Now, last thing I want to talk. I mean, there's also a couple of theories like Rankine and Coulomb. Rankine's theory um, assumes that there is no friction between the wall and the soil at that interface. There's no friction. That is Rankine's theory. That means your resultant will always be in that direction when the backfill is like that. Whereas Coulomb's theory, Coulomb assumes a little bit of friction between the wall and the backfill, and his reaction will be slightly inclined. Okay. And Rankine's theory, even if if let's say Rankine's theory, if backfill is inclined at an angle beta, then your resultant force will also be inclined at an angle beta on Rankine's theory. And Coulomb's theory, you will have to calculate that value, which is based on the angle of internal friction and your the angle of your slope there. There are formulas to calculate all that, and you have information of all this in your PE handbook. But then I just want to bring it up. Okay, so I think we talked about all those details. So let's see if we can do a problem and in today's session there. Okay, so let's take a retaining wall. So here is my retaining wall, right? Then it's like that, and then the height of from here to here 8 feet. The thickness is 1 foot 4 inches of that this one. Retaining earth on one side, right? Gamma soil is 120 psf. Gamma concrete, all this is concrete, right? Retaining wall is made out of concrete, 150 psf. Earth pressure coefficient, they have given it to us as 0.4. Dead load, that means there is a dead load UDL. Remember the UDL that I was talking about? Is uniformly distributed dead load acting on it. W dead is 150 psf, and there's also live load UDL acting on it, right? So there's also live load acting on it, UDL, right? How much is that value? That value is Q live or W live is 90 PSF. Okay, so live 90 PSF. Now we have been asked to do two things. Number one, determine the shear, critical the shear, the shear. That means shear at this interface, at the shear at top of the footing. Okay, and also determine the flexural strength. So shear, determine the flexural strength. Again at the same interface, because this is where the flexural maximum bending moment is going to happen. So at the top of the flange. Okay, and then I think we're also asked about, there's another question here. So second thing is maximum soil pressure. Now if you have something like this, then you will have to there might be soil pressure, right? And the soil pressure might be might be distributed or something, like maybe it is maximum. We'll have to calculate that, but maybe it is maximum there and the minimum there, something like. So this might be Q max and this might be Q min. So you have to calculate those two values. To calculate those two values, you need to know, again we talked about this in detail as to how to calculate earth pressure and all that, but the idea is to find out a resultant. So let's say you have a let's say a footing like this. The idea is to find out a resultant force and a moment, resultant P and then a moment value, and then you can find out that using P by A plus P times of E by Z, you can, this is the value of your Q max, right? And then P by A minus P times E by Z, this is the value of Q min, right? So the max might be happening, in this case max might be here, min might be there. So this is your Q max and this is your Q min, right? It's happening like that. Okay, so that's a pretty straightforward formula, but then how do you calculate your P? How do you calculate your M? How do you calculate your eccentricity in a practical setting like this is the question. Okay, so that's what this example is about, trying to translate all those concepts into numbers, and then we go from there. Okay. All right, so let's get started. We will draw this one more time, something like that, something like this, something like that. There is soil here. So let's calculate. To calculate our resultant piece, you will have to calculate individual piece. So one component might be due to this one. This is weight 1. The other component of weight is due to the footing, weight of the footing itself, that is W2, and it will act at the center of the whatever width is. The other component is W3, which is the weight of the soil itself, and that will, we are talking about soil within within that zone, right? Not, we are not talking about soil elsewhere in the next town there. Okay, and then I don't know if I can move this, but then let's see if we can. No. Okay, anyway, I'll experiment with that later. But then for now, I'm going to erase this side here, because we will, so this, but so these are the weights, and there are also earth pressures acting, right? So you have from here to here, you have one earth pressure acting like that, because you have another earth pressure because of your dead load and live load, remember? And then this is might be due to dead load, this might be due to live load. And I think in the pressure distribution, we were asked to, I don't think I made that clear, but in this question, we are going to ignore the effects of these things. This is Ka times of your Q live. This is Ka times of your Q dead. For just for the dead load or the unfactored, for the soil pressures, we will try to ignore the effects of these two, meaning we'll only consider the effect of the weights and the force there. Okay. Now, how much is that? This is Ka times of gamma times of the total height, not just height till here, but then this entire height from here to here. Okay. So let's calculate W1. W1 is nothing but it is the stem is 1 foot wide. So 1 foot times of 1 foot normal to the screen times of 8 feet height. This is 8 foot, 8 feet, 8 feet times your gamma concrete. Okay. So that is 1200 lb per feet. For which feet? Foot normal to the direction of the screen. W2 is 6.5. W2 is this one. This is I think in the problem statement is 6.5 feet. Okay, 6.5 feet. 1 foot normal to the screen. 150. Sorry, how times how thick is this? 1.33 feet, right? So that thickness is 1.33, 1 foot 4 inches or something like that. 1.53 times your weight of concrete. That is 1296.75 lb per feet cube. Now you calculate W3 is the weight of the soil within that range. So what is that width? That width is 3.5. How do you get 3.5? You take I think from here to here the problem statement should be given. This is 2 feet. This is 1 feet. So 2 feet, 1 foot, 3 feet minus 6.5. 6.5 by 2. Right. So let me recalculate 6.25. Sorry, 6.5 by 2 minus 3 minus, sorry, 6.5 by 2 minus 2 minus half. Okay, just to be clear, that width there, this is from here to here, is what your 6.5 minus this 2 feet minus the thickness of the wall is another 1 feet. So the whole thing is 3.5. So this width is 3.5, height is 8 foot times your 1 feet normal to the screen times your density of soil. Okay, so that is 3360 lb per feet. lb per feet. Okay, so those are the three forces vertically acting. That means how can we find out the resultant? Resultant is nothing but W1 plus W2 plus W3. So you add those three values, 58, 56.75 kips. That is your resultant force. Where is that acting? W1. So you find out where x1 is the distance from which the W1 is acting. So this is 2 plus um, half. So x1 is 2.5. What is x2? X2 is from this face. Where is W2 acting? 6.5 by 2. So that is 6.5 by 2, 3.25. X3, what is X3? The X3 is the distance from this edge again to the CG of that force there. So you find out that one and that will be 4.75. Okay. Why do you want X1, X2, X3? We want to find where the resultant force is acting. That is nothing but W1, X1 bar, X1, W2, X2, W3, X3 by W1, W2, W3. So that is nothing but you substitute, plug and chug, use all these W values, W1, W2, W3, X1, X2, X3. You find that your X bar resultant is acting at 3.956 feet. From where? From that extreme edge. Okay. So that's how I found my force and I found my resultant. Now let's we need to calculate the moments. We need to, how do you calculate your moments? You need to, okay, so I think we went off the path a little bit. Let's calculate the shear force that is acting. So here is the footing like that. First part of the question was referring to the shear that is acting there. Okay, so to calculate the shear, you need to know the you need to capture the effect of the lateral earth pressure, because that is causing a little bit of component of shear is from that. The component of shear is from your uh, live load, which is uniformly distributed. Why is it uniformly distributed? Because the live load itself is uniformly distributed. Now a portion of that is also from your dead load, and that is uniformly distributed across the height. Why? Because it is the dead load itself is uniformly distributed. Okay, now what is this value? That value is nothing but your Ka times your gamma of the soil, right? And your height is not just this height, but this entire height. Okay, so that entire height is like 9.33 feet, I guess. Okay, but in this case we are interested only to find the shear there, so that component will be um, that is the height that we are interested in. Okay, so because we are interested here, then we will consider the height as 8 foot. Okay, so what is your Ka? Ka is given in the problem statement as 0.4. Okay. Now, one thing to note is we are calculating the factored shear. The factored shear has to come from factored lateral earth pressure, and the load factor for lateral earth pressure, which is considered as H, is 1.6. Okay. So though this is dead load, and this is where I did a mistake. Let's say this is a component of dead load and this is the component of live load, Ka times that. The effect of that, though this is dead load, but this comes under the H category, right? So this is not dead load. This is the lateral earth pressure because of the dead load. This is the lateral earth pressure because of the live load. And lateral earth pressures all group under the H category. So your load factor is, to calculate your factored shear, is 1.6. Okay, so let's put that 1.6 on this side here, and then start working out all our lateral pressures. So the first lateral pressure is due to at that location, and that location, what is the area of this piece? Area of that piece is my pressure. So half Ka, sorry, Ka is that much, gamma is 120, H square is that much. Okay, so that is because of this. And then you have another 1.6 times. So this fellow here, the Ka value is 0.4, and the area of the pressure distribution till there, right? So that means we are talking about uh, that area there. How much is that? Um, that is your Q dead is 150 psf. Yeah, Q dead is 150 psf times your 8 foot height. Okay, why 8 foot height? Because we are calculating forces there. Now the third component is due to live load, 1.6 factor again, but 0.4 is my this one. My area of the pressure diagram is, then live load is 90 feet. So QL is this, QL is 90 times your height, which is 8 feet. Okay, so you do all those calculations, your VU will come to 3686.4 lb. What is VU? Factored shear. Why is it factored? We are factoring it. What is the factor? 1.6 is the factor. Why is the factor 1.6 for dead load? Because this is not dead load. This is the lateral earth pressure caused by the dead load. Okay, so that's why it still comes under the category of H. What is this 1.6? This is for the live load. Why are we multiplying it with 1.6? Because this is the lateral earth pressure caused by live load. and not live load itself. And so you doing all those factored values, and you come up with your factored shear at this location. Okay, and you can also calculate the factored moment at that location, which is mu, right? How do you calculate mu, and what is the critical location? Here is the footing. The critical location is there, right? And how do you calculate those values? You calculate the this is the earth pressure, so you calculate your resultant, and then um, so this is due to earth pressure due to soil. This is due to the surcharge, live load surcharge. Again, K active live load uniformly distributed across the entire height, correct? Same thing here, Q Ka Q. Let's say this is dead load, uniformly distributed across the entire height. Okay. Now we want to find out our moments there. Okay. The same thing for mu. The factor is still 1.6. You're calculating the factored moments. 1.6 times what is this fellow here? Um, right. For that, again you're calculating the moment here. So we are considering everything till there, till there, till there, right? So what is that value here? Half times of Ka, sorry, Ka is 0.4, gamma of the soil is 120 into h square, h is 8 square. So that is your force times where does it act? It acts at a distance of h by 3, right? So h is 8 by 3. So that is the moment cost due to the first component there. Moment cost due to this one, again a factor of 1.6, Ka is 0.4, Q live is 90, correct? And this is caused because of, so Q live is 90 times of height is 8. This is the area, where does it act? 8 by 2, mid height. So this one, because it is simple rectangle of height h, it acts right there. Okay, what is the third component of the moment? It has to be factored by that much, but this time it is due to Ka, live load 150, 8 is my height, so that is the area of that portion there. And where does it act? 8 by 2, right? So that's the moment. You calculate all that, you come down to 11.5 kip feet, mu, so not nominal, mu. So that is your uh, mu value there. Okay. Okay, so that's about mu. Now the last thing, we have to find out our earth pressures, right? So we have a, so let's draw the story. We have a footing like this, correct? We have our resultant P. So here is this is the width of the footing, which is 6.5, correct? So that means the centroid of the footing is at 6.5 by 2, roughly there, correct? Whereas our the x bar, that means the resultant force because of W1, W2, and W3. Remember W1, W2, and W3. That was acting at x bar as x bar of 3.956 feet. From where? From this reference point, right? So that means my resultant force is somewhere here, and this distance is 3.956 feet, correct? So that means the eccentricity is the distance between the centroid of the footing and the result line of action of the force. So that distance is my eccentricity, and you subtract 3.95 from by 6.5, so 6.5 by 2, you will get 0.706 feet. So there is a P, and that P is acting at this eccentricity, right? And then there is also a moment being caused, moment in this direction being caused by my this is moment 2. There is a moment 1 which is p times of e. Okay, so there is p, there is p times of e, which is one bending moment which is acting clockwise, which is acting like that. P is acting downward, and there is another moment because of lateral earth pressure which is to the left and causing an anti-clockwise moment. So that is your m2. Why is this m2? I'm calling this one as m1. This is the pe moment, whereas this is the lateral earth pressure moment. So to calculate your earth pressure, you need to consider all these three, the effect of all these three components together. Okay. So now we know P, we know P eccentricity, so we know PE. So let's calculate M2. Again, M2 is caused because of this particular, um, I mean, earth pressure acting here, right? So now you're trying to calculate M2. You're not trying to calculate the moment here, but you're trying to calculate the moment at the end of the footing. So you take the entire height. That height will be H1, which is 8 plus 1.33, 9.33 feet. So that's your total height. So what is this one? This is your Ka gamma times of H. Ka is 0.5, sorry, 0.4, 0.4. Gamma of soil is 120. Height is 9.33 feet. Okay. So what is the moment caused by that? You need to find out the force caused by that and then multiply it with the lever arm. So what is the force caused by that? That force is half Ka gamma. This is zero point 0.4. Gamma is 120 h square, 9.33 by 2. That is your, sorry, h square. So that is your force. Where is that force acting? Acting at a 9.33 by 3. Where is that? That is from here to here. That is your 9.33 by 3. That's the lever arm. So this is the force. That's the lever arm. Multiply that. You get your moment as 6497.33 lb feet. So that is the moment acting in that direction. Okay. So now again, why are we calculating all these three? The earth pressure at the bottom of the soil here is a function of the axial load coming onto it, a function of the effect, I mean the PE moment, which is because of the resultant acting at an eccentricity from your base, and then it is also due to your M2. Okay, we only realize that the PE moment is in the, because your P is acting, resultant is acting here, which is to the right of the CG. Your moment is in this direction, PU moment is in that direction, whereas M2 is pushing like this, so it is in the opposite direction. So respecting those directions, what we can do is we can calculate the stress at A and stress at location B, right? So one of it will be maximum, one of it will be minimum. So at location A, you have your P by A uniform stress, right? Why is it P by A? You are assuming that the resultant is acting. Um, so let's make that thing a little bit clear. So you have a footing like that, and uh, your P is actually acting here, the resultant P, right? PR. But we can replace that. Whereas the center of gravity of the footing is here. Why is the center of gravity there? Because it is 6.5 by 2. This is 6.5 by 2. That is the center of gravity of the area, centroid of the area, right? So we can treat this scenario as if the force is acting not at the not at that eccentricity, but acting at the centroid. So let's say this is the centroid. You can treat that the force is acting at the centroid, and then you can treat this as a scenario wherein that additional p times of e, which was acting here, this additional p times of e is a bending moment acting, m is equal to pe moment acting at the centroid. What will this enable? This will enable us to calculate the stress here as a uniform stress, and that value is nothing but your P by A, because there's no eccentricity is acting at the centroid, that is a P by A, correct? And then it will also allow us to calculate this the uniform, so the moment here, which is obviously maximum there and less here, correct? So that is the soil pressure due to that M. And there is also another component which is M2, and then that M2 is acting like this, right? Your M2 is acting like that, which is acting, that means you have maximum, that means you have maximum pressure here, minimum pressure there. So you can calculate those three components. So finally, the stress at this point is the sum of that, is a sum of your M by Z from here, and is a sum of your M2 by Z from here. The only thing is you need to take the sign into account properly. So this is P by A, compressive stress, right? At this point, PE is causing a moment like this in this direction, that is, it's going to lift off. That means the stress will be less there, stress will be more here. So it is going the other way. So P times of E by your Z plus the effect of this fellow here. He is pushing this area, so there'll be force will be, this will be compression here, tension there, let's say. So that is M by Z. Okay. Now stress at the location B, P by A is still compressive. Okay, and this PE by Z stress at location B is location here, right? We're talking about this location here, location B. P by A is still compressive here, whereas here appears to be compressive. So this is P times of E by Z, right? And then at this location, because of this moment, looks like there is a lift off. So minus M by Z. Okay. So what is your section modulus? Now looking at the footing retaining wall from the top like that, let us say we consider 1 foot in this direction, retaining wall. So obviously this is my wall, right? This is my 6.5 feet, right? The bending is happening about that axis, correct? So my Z is nothing but BD cubed by 12 times of D by 2, right? So that is D square by 6. D is 6.5. So your section modulus is nothing but 6.5 square by 6. Okay. So if you substitute those values here, you will find out, for example, at A, you have a P of 5856.75. Area is 6.5 by 1, right? Minus PE. PE is still 5856.75. Eccentricity, we found out that to be 0.0706 divided by 7.041. That is your section modulus. This will be 7.041 inch square section modulus. Okay. PE by Z plus this fellow here, your moment due to, sorry, bending moment due to, or lateral bending moment due to earth pressure is 6497.3. We calculated that by section modulus 041. Okay, so that is at A, and at B it is 5856.75 divided by area 6.5 by 1 plus this value here 5856.7. This is P times of E 0.706 divided by 7.041, right? Minus this value here, this is 6497 due to earth pressure, right? By M by 7.041 is your Z. Okay. So you do that, you find out that your maximum value will be this one, and that is equal to 0.56 KSF. Okay. Sorry, minimum value is that, whereas maximum will happen here. This, and if you calculate that one, it will be 1.236 KSF, right? So that means the final pressure distribution is like, because of the force and the eccentricity is maximum here, minimum there, maximum value 1.236 KSF acting like that. Soil is naturally pushing it, and the minimum value did not go to 0, causing no lift off, right? Causing lift off KSF. This does not go to 0, so that is the minimum value there. Okay. So we rushed through the example a little bit, but then the idea is simple. Idea is to calculate. Let's talk about this one real quick. Here's the problem. The idea is to just divide them into components. So I think so what we did here is we are trying to calculate weight 1, weight 2, weight 3, weight 1, weight 2, and weight 3, which is the weight of this stem here, that is W1, this is W2, weight of this concrete slab, W3 is weight of this soil here, right, soil in that block. And then we are trying to calculate the earth pressure component, right? So W and W3, you find the resultant as that much, and the resultant is acting at this particular distance from the face of this footing there, right? Then we calculated the shear at this point. We calculated the shear based on plotting the diagram, right? Now we did not take the entire 9.33 as a height, but we took the 8 foot as a height because we are calculating shear at that location. Shear is nothing but the area of the diagram, but because it is factored shear, we multiply it with a factor of 1.6, 1.6, and 1.6. So shear contains three components. One is due to earth pressure, one is due to the imposed dead load, one is due to the imposed live load. Same thing with moment. Moment contains three components. They have to be factored. That's why you see a 1.6, 1.6, and 1.6 there. Moment due to earth pressure is due to this triangle here till that red line, right? So and then multiplied force with lever arm. Moment is due to area of this triangle here, sorry, rectangle here, and then multiply it with the lever arm, which is 8 feet by 2. That's what is happening here. This one here is a moment due to dead load, and you're multiplying with the lever arm there. So you find out the final moment. Okay, but now you have to find out your earth pressure. So we are trying to find out our resultant P, and then we are finding out our eccentricity. So the effect is, if you then you can replace the P as if it is acting at the centroid causing uniform pressure, and you can replace the moment acting at the centroid, and the moment value is nothing but P times E. But in this case, we also have another moment which is going in this direction because of the lateral earth pressure, because lateral earth pressure is pushing from right to left here. So you account for the stress due to the axial, or stress due to P, the stress due to PE, the stress due to your moment, and then you algebraically add them or subtract them based on proper sign convention. Okay. So and then you will find out that on one side you will have slightly higher stress than the other side, and based on that you draw your pressure distribution. Okay, so we talked about a bunch of things today. We did some foundation problems. Um, we talked about retaining walls. We tried to do a worked out example on retaining wall, and we also did a worked out example on footings. Right, hopefully this helps. Thank you.